Okay, what you can there are a few things that you can observe with these two diagrams. Yes or no? Okay, so like what I've written. Okay, what I've written is when shear force is equal to, well, shear force intersect the when the curve, or when the graph in the shear force diagram intersect the zero shear stress line, right? Like what I mentioned, there is a possibility I can't spell, no, ability that the bending moment is maximum or minimum, right? You guys saw that, right? Right. So the next thing that you observe, right, that we observe is this. I think the next thing is so when there is a, no, wait, okay, so between A to C, right? So between, so let me, so this is A, right? A, B, and this is C, right? So between A to C, right, you realize that we have a distributed load, right? Evenly distributed load. Okay. So the shear force, when it's evenly distributed load, the shear force has a linear gradient, right? And the bending moment, and if you look at the bending moment at this point, right, it's a what? It's a curve. Yes or no? So the shear force in terms of distributed load is a straight line, linear gradient. The bending moment will be a curve. So that's the next thing we discover. So when there is a distributed load,
Sir, are we gonna have a situation, say if the maximum bending moment isn't at a defined point, like say in your example it's not at 2.4, it'd be like 2.3. Are we gonna have a situation where we have to take the derivative of the
yes,
function defined?
yes,
Okay.
that's how you do it. Okay, so what Sean just mentioned is, in order to get this, right, you always have to get Vx is equal to 0. And Vx is equal to what? dm by what? dx. That is later, okay? That's later. After your term test come back, we're going to do more of it. Now I'm going to sort you out in terms of how to form the equation and how to do the shear force and bending moment diagram, okay? Sean, you are right, okay? So when there's a distributed load, right, for this case, evenly distributed load, okay? So this is when we talk about point A to point C, right? Between point A and point C, the shear force, right? The shear force has a linear gradient. Okay, has a linear gradient, and the bending moment is a curve, right? Like what you have seen. And then when there's a point load, okay, so there's a point load from C to D, yes or no? So when there's a point load from C to D, so what you have is the shear force diagram is constant, whereas the bending moment is a gradient. Okay, so another trend that you can see. Okay, so when there is a point load only, So this is from point C to D. Okay, so the shear force, okay, the shear force is a constant. So constant means that gradient is equal to 0. Okay, and the bending moment you guys should learn this in math, okay? Has a bending moment, has a linear gradient. Now, the last point, which is the most important, okay? The last point, which is most important. So I want you to observe this. Okay, I'll try to use, I want you to observe this line. Okay, this yellow line now. Okay, and this, okay, right. So what you see over here, right? What you tend to observe over here is this. Okay, the shear force over here has what? The shear force over here has negative magnitude, right? And what you see in the bending moment diagram, again from 0 to 0, the slope is what? Negative. Okay, so the gradient is negative. Okay, so now let's look at the time where it becomes positive. So down here at B over here, okay, so at B it has no gradient down here, right? It has no, but later on, right, the gradient from here to here is positive, right? So magnitude is positive. So over here, the magnitude is positive, right? So the gradient on the bending moment, oh, okay. The gradient on the bending moment, okay, where I'm going to shade in blue. Now the gradient is what? Positive, right? You have positive. And then at 2.4, right? At 2.4, right? Where you have what? You have zero, where you have zero magnitude in shear force, your gradient is also equal to what? Is equal to 0, right? So when this part over here is negative, right? The gradient over here is also what? I can't spell all of a sudden. Negative. So a thing to observe over here is this. Okay, so what do we see? Okay, the shear force magnitude right, is related to the bending moment gradient. So what do I mean? So if we look at the shear force, and then when you look at the bending moment, so we realize, okay, bending moment, come on. Right, so when the magnitude is positive, the gradient has to be positive. When the bending moment, the magnitude is negative, right? The gradient will be negative. Okay, so these are the things that you have to know. Okay, so that's why it's not just drawing a diagram. What does it actually means? Okay, and as I mentioned before, we are letting the math, okay, to solve out the equations. Okay, so the math, you don't need point C is not at 2.4. It is at 3.2. Point C. Yeah, 3.2. Taeyong, you're right. So did I do something wrong? So 3.2 over here represent the 3.2 over here, right?
Yeah, in the last one, in the last page,
The last?
page 5, on the shear force diagram.
So the shear force diagram, 0.80, 3.2 minus 40. Is this the point you got issue?
No, I mean when you go to the page 5.
Page 5.
Yeah, so on the shear force diagram, so your pointing is C on the 2.4, but it's supposed to be 3.2.
Ah, yeah, you're right. 2 times. So this is at point C. Okay, thank you for telling me. Okay, you get 2 bottles of soju when I see you. Okay. Okay, so where was I? I just led up to read. Can anyone recall where was I? I can't remember now. Yeah, but okay. Anyway, I can't remember where I finished off. Okay, so the math. Okay, the math is the one to verify. Okay, the math, like what you can see over here, the math is the one to verify how your diagrams, your shear force and bending moment diagram will look like. Okay, now I'm so over here you just see evenly distributed load. Okay, so evenly distributed load, right? Like what I told you, I'm going to cover this. So at a very quick way at one. Okay, so for evenly distributed load, right? If this is X, right, and you have evenly distributed load, so this is omega, right? For the equivalent load, it is very straightforward. So if this is X now, okay, so this will be omega X. This will be X over 2, right? So we know that. Now for a gradient, you have to be careful. Okay, it is okay. Jenna or Taeyong, I only can give you the hint of how to do it, and it's not difficult for the shear force or for the sketch for the normal stress. Okay, I can give you a hint and how to do it, and I think the hint will be good enough for you. Right. So now this is an evenly distributed load. Right. So this is omega. Right. So the function of the gradient or the function of the distribution okay, so if this is in terms of X, okay, the function of the distribution is equal to omega as a function of X, right? And then the slope, sorry, this one, the slope is equal to L, sorry. Okay, so this is equal to omega over Lx, okay? Why omega over Lx, right? Because this equation over here is omega as a function of x. So the gradient is omega over Lx, okay? So this is the gradient. So the gradient is equal to change in y over change in x, okay? So this is equal to change in y is omega, change is L is L, and then is a function of x, okay? To get the equivalent load, right? To get the equivalent load, okay, so it is omega equivalent. You have to integrate